Let's take a look at another example. Say you're working as a civil engineer and you're trying to determine the effect of curing time on the compressive strength of concrete blocks. You collect a sample of 10 blocks cured for 2 days, and you collect a sample of 13 blocks cured for 6 days. The compressive strengths of each block in megapascals was determined using the strength testing. Okay, so we've got 10 blocks cured for just 2 days and 13 blocks cured for 6 days. We use some kind of strength testing approach to determine what their strengths are, and here they are in MPa. Okay, so one of the first things that we need to do is set up our hypothesis, and we want to know if the strength is greater for blocks cured for 6 days. Okay, so if we cure these things for a longer period of time, is the strength greater? Okay, but let's say we can't make the normality assumption here, so we have to use a non-parametric technique. We're comparing the distributions of two different populations. We're going to use a non-parametric technique. So hey, let's use the Wilcoxon rank sum test. Okay, so our hypotheses are going to look something like this. D1 and D2 are the same. Okay, and let's call this D1 and this D2. Okay, population 1 and population 2. So the null hypothesis is that they're both the same, and we want to know if the curing time for 6 days leads to a longer strength. Okay, so we always refer to this in terms of population 1. So we want to know, does D1 lie to the left of D2? Okay, we want to know if this is more than this. If this is more than this, then this lies to the left of this. Okay, so, and we always give this in terms of D1 relative to D2. Okay, so is D1 the curing strength if we cure, or the strength for the concrete blocks if we cure for 2 days, does it lie to the left of this, meaning that this is greater? Okay, so we take these and we order them from smallest to largest, retaining whether they were cured in 2 days or 6 days. Okay, and then we would rank order all of these. Okay, so here this has rank 1, it's the smallest. Rank 2, it's the second smallest. And we don't have any ties in here. Okay, so we're going all the way 1, 2, 3 up to 23. 10 plus 13. 10 observations here, 13 here. So 23 would be the largest rank whenever we combine all of these together. Okay, so we know what all the ranks are. Okay, now we separate these back out into 2 days and 6 days, and we find the rank sum for each one of those populations. Okay, rank sum for the curing for 2 days just happens to be 65. And the rank sum whenever we cure for 6 days, that ranking, the sum of the ranks is 211. Okay, so remember what we're doing here. With the parametric test, we would take a look at, is the mean of this different than the mean of this? Okay, is the mean of this bigger than this? Okay, but if we can't assume normality, then we have to come up with a completely different approach. Okay, so we're not going to compare the magnitudes, we're going to compare the ranks. Okay, you would imagine that if these were roughly the same as these, then their ranks would be roughly the same. Okay, these are not roughly the same. So is this sum of ranks significantly more than this sum of ranks? If so, we're going to reject the null. Okay, so our test statistic is T1 minus N1 times N2 plus N1 times N1 plus 1 all over 2 in the numerator. And in the denominator, we've got the square root of N1 times N2 times N1 plus N2 plus 1 all over 12. Okay, so this is our test statistic. We just have to plug in numbers. It's just arithmetic from here. Okay, so we know what T1 is. That's 65 minus N1 is 10. Let's write those out as well, just so we're clear. N1 here is 10. N2 is 13. 10 observations here, 13 observations here. So 10 times 13 plus 10 times 10 plus 1, all over 2, divided by the square root of 10 times 13 times 10 plus 13 plus 1, all over 12. Okay, just arithmetic from here. That test statistic is negative 3.41. Negative 3.41. Okay, so we go over here, go to our z distribution. Here's our test statistic. It's negative 3.41. This right here, that area, is the p-value. Okay, we have a lower tail test here. Okay, this is just a one-tail test because we explicitly want to know if D1 lies to the left of D2. And if it lies to the left, we're going to reject in the lower tail. Okay, if we go to our tables, we're not going to find 3.4 in a row and 0.01 in the column. Okay, our table doesn't go this far out. Okay, so that tells us one thing, that this number is quite a ways out there. 3.41 standard deviations away. This number lies 3.41 standard deviations away from what we would expect it to if these two distributions were the same. Okay, so that says a lot, right? That means that this number is probably going to be rejected. This number and this number, these two numbers are quite a bit different from each other. 3.41 standard deviations, this number lies from what we would expect it to be. Okay? So we can't use the tables, or we can make some assumption based on the table, but let's just use Excel, okay? So we're going to use the norm sdist function, okay? And we're going to input our value of negative 3.41, okay? For the norm sdist function, we can input a negative value here on the axis, and it works just fine. Okay? It gives us the cumulative probability up to that value, which is exactly what we want. Okay? And if we work that out in Excel, or use Excel to work it out for us, we get this number. Okay? 0.000324. Okay? Very small p-value. Much smaller than any alpha you would ever choose. We would ultimately reject the null and conclude that D1 lies to the left of D2. That is, the curing strength over here, the central tendency of curing strength, the central tendency for strength after we've cured for 2 days lies to the left of the central tendency of strength after curing for 6 days. Okay? Curing for 6 days leads to a longer strength than curing for 2 days. And we have an answer that we're quite confident about.